Thanks everyone for coming to attend this introduction to input-to-state stability. This is a topic I've been working on for many years now. Not always, not full-time really, but yes, I've developed quite a bit of experience in this topic in the past really 20 years now. So let me start. I will first of all explain some background on stability. What is stability? How can we define stability? At least how classical stability was defined, some motivations, of course. And then I will go on trying to explain what is input-to-state stability, in what respect is a bit different, but in fact really trying to bridge a gap between two different types of stability definitions that we will see later on. Then I will explain how this stability can be characterized and tested by using the Lyapunov-like techniques, and show how I feel this concept is quite natural, in fact, introducing many types of related notions and equivalences that can be proved with respect to input-to-state stability. Talk a little bit about systems, interconnection, and modularity, which was one of, in fact, of the things that pushed the introduction of the concept in the first place. And then point to some possible directions that have been pursued in really transforming this notion of input-to-state stability to a whole paradigm to study systems theoretic concepts. And so, first of all, what is stability? So, in general, the word, let's say informally, it's associated to some kind of notion of robustness of behavior, maybe of a dynamical system, with respect to perturbations. And this perturbation can have different nature. In fact, we could be talking about exogenous disturbances entering the system, or we could be talking about initial conditions, so initial states that are perturbed with respect to some kind, again, of nominal situation of interest. Or that could be, for instance, also parameter changes, either time invariant or either time varying, in which case perhaps you would see them as disturbances. So, in fact, there is then many types of perturbation and also many ways of deciding whether something is robust with respect to this perturbation. For instance, you could think of characterizations that are only concerned with what happens for large times, asymptotic in time characterizations, or you would perhaps be interested in knowing what happens during somehow the transient. So what happens even for short time, whether you've got some kind of robustness. Or you might want to also measure the amplitude of perturbations as well as the amplitude of the deviations that this perturbation induce from the nominal behavior in terms maybe of signal norms or other types of concepts. So because of all these choices, in fact, there is, at least in principle, the possibility for a big, really landscape of different stability notions. And in fact, to a certain extent, there's many such notions. And we are going to talk specifically about nonlinear systems, so that already gives us a very broad set of possible behaviors, and so many stability concepts as well. But what are practical implications of this situation is that, of course, stability is desirable in many applications, for instance, but it's also important to understand what kind of stability really is needed for different applications, exactly because of this wide variety of options. And some forms are, of course, stronger than others. They have stronger implications, so perhaps they would be more desirable to achieve certain objectives, but of course, then they're harder to either achieve by design or infer by analysis. And so one has to see what can be done, what can be proved, what are reasonable stability concepts that can be, in fact, shown for the systems that we're considering. So I will introduce some classical approaches because, in fact, input-to-state stability was very strongly influenced by these two classical approaches, and in a certain sense, as I said before, is attempting to bridge the gap between the two. So the first approach is the so-called internal stability by Lyapunov, initially, let's say, formulated for autonomous systems, so systems described by state space equation, first order state space equation, x dot equal f of x. In our presentation, x will be a finite dimensional vector taking values in Rn, so Euclidean space, and I will be denoting solutions at time t, maybe in this way. So x of t is equal to phi of t x0, where x0 is the initial condition and t is the current time. And later on, I will be also dealing with systems with input perturbation. So there will be an input, exogenous input appearing here, and that will also come as an argument in my phi mapping, let's say, in order to be able to express the solution at time t from initial condition x0 and for a particular input signal that I am considering. So in internal stability, Lyapunov stability, the robustness property is really defined with respect to perturbations then in the initial condition. So there is one initial condition that is considered to be of interest. This is perturbed, and we look at the deviation of the corresponding solutions with respect to the nominal solution. Instead, in external stability property, we are basically already by construction dealing with a system with exogenous input. Very often this can be modeled as an operator, so some kind of mapping from an input space to an output space, maybe causal. And one way to express stability for this type of setup is to, in fact, look at norms of input, which are in this respect looked at as disturbances, and corresponding norm of outputs. For instance, you could think that y equals 0, output equals 0 would be your nominal behavior, and then you would want to make sure that if, for instance, the norm of your perturbation is bounded, then maybe also the norm of your output is bounded in some suitable sense. So, going a little bit more in the details of these definitions, because it will be helpful also for the definition of input-to-state stability. One could, for instance, specialize the notion of Lyapunov stability to the simplest possible case, which is the case of a nominal solution, which is an equilibrium point. So a point xe such that the corresponding solution phi t xe is equal to xe for all times. And then we can say that this point is Lyapunov stable if this implication holds. So this implication, I can read it out. Many of you will have seen it already. For all epsilon bigger than 0, there exists delta bigger than 0, such that if the difference between x0 and the equilibrium is smaller than this delta, then the deviation phi t x0 with respect to the equilibrium is less in, again, norm than epsilon for all non-negative times. So what this is saying, essentially saying that small perturbation in initial state, they imply small deviations from the equilibrium for non-negative times. And in particular, these quantifiers effectively they tell us that sufficiently small perturbations, so there exists a delta, imply arbitrarily small deviations. So we are able to pick this small enough so that we can make the deviation arbitrarily small. So this is a local stability concept and characterizes the behavior of the system somehow in a neighborhood of the equilibrium. Yes, is there a question?
No, David, I think it was just someone joining a few minutes late. I just let them in. I think that's all it was.
Okay, so that's okay. It's all right. So feel free to interrupt if there are questions, by the way. Yeah. Actually, I think it's interesting to be interrupted. So I get a little bit of feel of where the audience is, because it's quite hard, obviously, like this. But okay, so if there are no questions, I'll move on then. So this notion of stability is normally complemented with another property, which is called attractivity, normally. And in particular, this notion has to do with what happens for long times to the system when perturbed. And in particular, the equilibrium, again, if we look at equilibrium nominal behaviors, we can call it attracted if for some delta positive perturbations x0, which are in a delta neighborhood of the equilibrium, basically result in solutions which converge. Again, for t that goes to infinity, converge to the equilibrium. This is called local attractivity because this property is only asked for sufficiently small perturbations, where we're talking about global attractivity when this is in fact required for all initial conditions within the state space that we are considering. And so this is the corresponding behavior. So, of course, practically this means that the nominal behavior is somehow restored, at least for long enough times, either for sufficiently small or for arbitrary perturbations. Notice that, okay, this property is in fact unrelated to Lyapunov stability for nonlinear dynamics, in the sense that it's possible to build examples of equilibrium of dynamical systems which enjoy, for instance, attractivity but do not enjoy Lyapunov stability, and vice versa. So they're really two independent concepts, but together, they are used as a very common notion of stability for equilibria. In fact, there is a special name for an equilibrium that enjoys both, and it's called asymptotically stable. So an equilibrium is asymptotically stable if it is Lyapunov stable and attractive. And in particular, depending on the version of attractivity that we are assuming, we have two different types of property. We have local asymptotic stability or global asymptotic stability. Both are of interest. I would say that for us in the following discussion, we will see that input-to-state stability is really a notion that focuses on global properties. So it's the global version of this property that will be particularly of interest to us. So one of the things that is also quite useful to remark is that not only, of course, asymptotic stability is very commonly used notion of stability for linear and nonlinear dynamics, but that the formulation that I've given, which is somehow the classical formulation, is perhaps not the most efficient in terms of being synthetic and its meaning being apparent, I would say. So there are alternative formulations that use what are called comparison functions. Later on, I will introduce these comparison functions because they provide a very effective way of expressing stability notions. But before doing that, I would like also to introduce the other somehow main leg, let's say, of classical stability formulations. We've got Lyapunov and we've got input-output stability. So I want to introduce also input-output stability. So the idea is to introduce concepts for operators mapping input to outputs, which could be, for instance, formulated as some form of so-called bounded input, bounded output stability notions. So the idea is that you want to measure your input and make sure that whenever this is bounded in some sense, then the corresponding output is also bounded. Yes, is there a question? I don't know, perhaps not. I see that someone is requesting control, but feel free to ask.
I think someone said it was they clicked on something by accident, apparently.
Okay. It's all right. If anyway, you can stop me if you need to.
You're getting kind of semi questions.
Okay. So we want to make sure that whenever inputs are bounded, then outputs are bounded, perhaps using maybe the same norm and things like that. And so different signal norms are possible, for instance, LP norms, and one could ask an implication of this type, or maybe one could ask a finite gain type inequality between the norm of the input and the norm of the corresponding output. That should hold for all input signals applied to the system. Okay. I don't know why it's stuck now, my PDF. Maybe exit full screen mode. Okay. So one of the aims of input-to-state stability is in fact to bridge the gap between these two classical approaches. This allows, in fact, to clarify relationships between many different types of formulations. So the two worlds were kind of not talking to each other in a certain sense. We have internal stability and we have operators theory. So the setups are different to start with. So it would be nice to instead start with something that allows to deal both with inputs but also with perturbation in initial states, and see then what are the relationships between these different formulations. And it turns out that this exactly, in a certain sense, if you really work in many possible directions, can give you a framework for formulating and analyzing systems theoretic concepts of different nature, in fact, apparently maybe even unrelated to stability notions. And it really gives a taxonomy for denoting and recognizing such concepts, because we will see how this can be done. So we'll start with, in fact, classical input to stability, but see how this approach can really be extended to a certain extent. So, in order to give
David,
the definition,
I think someone had a question for you. I think
I missed that. Sorry.
Yeah, just
yes?
whoever asked the question, would you like to just
yes,
turn your microphone on and ask it?
So I'm happy to hear the question.
I did not get the concept behind the input signal norm in slide 9.
Yes. Sorry, I didn't.
On slide 9 of the
yes.
input to output stability, there was the input signal norm and different signal norms. And why are we taking norm of the input signal? Or is it just an example?
So there's different possible signal norms. I've taken an LP norm just as an example.
Okay.
And so you could do, for whatever norm you've chosen, you could decide that you may have a bounded input, bounded output property, or you may have a finite gain bounded input, bounded output stability, which comes in as an inequality of this kind. Yes. Okay. But yeah, it's an example, yeah, of a norm. Yes.
Thank you.
Yeah, you're welcome. Was there another question? Okay. If not, I will just go on introducing this notion of comparison functions. As I said, comparison functions, I said before, can be used really to provide very synthetic and quite intuitive looking and appealing definitions of stability concepts. So I will define them here and show them maybe with some examples. So the first type of comparison functions are of the following type. So they are functions that map the non-negative reals to the non-negative reals, and they are said to be positive definite whenever the function delta here is continuous, 0 at 0, and positive for all r bigger than 0. So, for instance, the function r over 1 plus r squared fulfills all of these assumptions. So it's continuous, 0 at 0, positive otherwise. So this is a positive definite function. A little bit stronger notion is the notion of class K function. This is a function which is positive definite as defined above and increasing. So for instance, the function delta r equal to r over 1 plus r would be a function of this kind. And finally, a function is class K infinity is called if it is both class K and unbounded, meaning that essentially the limit as r goes to infinity of delta of r would be equal to plus infinity. So examples of class K infinity functions could be the identity itself, r squared, of course, class K infinity, square root of r. So there are many such functions. So these functions serve many purposes we will see next, but one of the things they are used for is to define suitable shapes for Lyapunov functions, for their dissipation rates, and also for notions of gains that we might be using next. So let me perhaps, just to fix ideas, since I've given this example, just show you functions of this kind in a graph so that it will be perhaps more easy to remember the type of shapes that we're dealing with. So positive definite functions are functions that, this is not that great, but so they're supposed to go up somehow. They can have any behavior, in fact. All we need is that they're positive, okay? And it is absolutely important that this axis, they are defined for all r, this is r. On the other hand, class K functions, they are monotone. So for instance, something like this would be class K. This could saturate maybe. The next class, so this is class K, let's say. Next class instead has to be unbounded. So it looks maybe as class K, but does not saturate. And this is called class K infinity. So this is perhaps really the most useful concept, as it really plays the role of a gain, we will see in the definitions to follow. Okay, so let me go back to the presentation once this definition has been really shown also with pictures that probably is more effective. So full screen. The other type of comparison functions instead have sort of a different nature, and they're still functions from the non-negative reals to the non-negative reals, and they are called class L. What they fulfill is that these functions are continuous, positive in 0 this time, strictly positive in 0. They are decreasing functions, and lambda of t tends to 0 for t that goes to plus infinity. So the most typical, I would say, class L function is the exponential e minus t. So that's positive in 0, it's a decreasing function and vanishes to 0. On the other hand, class L functions do not need to necessarily be exponential in nature and decay to 0 exponentially. For instance, they can't decay to 0 polynomially, as in these two examples. What these functions are used for they're essentially used as a bound, as an upper bound for transient phenomena. So phenomena that may start out with some kind of amplitude at 0, but then eventually they decay to 0. So this shape is quite handy. And in fact, while the previous class of functions are used as notions of gain, these are used for transient phenomena. So you can combine these two notions into the so-called class KL functions. These are functions of two arguments now, both non-negative, which are essentially class K in the first argument for all frozen values of the second argument, non-negative, whereas there are class L in the second argument for all frozen values of the first argument, strictly positive. This is a minor technicality, as in 0, this would be equal to 0. So examples of these functions are this, for instance. This, I would say, is the most commonly used function of this form. So as you see, whenever you fix t, this is class k infinity, in fact, in R, as it is a linear function, so it grows linearly. And on the other hand, whenever you fix R, this is a class L function in T, so it decays to 0 asymptotically as time goes to infinity. This is one form, but again, there's no reason why the decay should be exponential or the growth should be linear, okay? So you could have many other types of functions, and in fact, they do not necessarily come as products like I've done it here. But what is interesting is that somehow we can again use this concepts, this type of functions, to characterize deviations of our system's solution from the nominal behavior. So let's have a look perhaps how this can be done, maybe for linear systems. Let's start from linear systems. So we take a finite linear system of the following form: x dot equal ax plus bd. And I use d for the input because I want to emphasize that this is a disturbance somehow. I use letter d for this reason. And essentially for linear systems, we know that asymptotic stability, really the most common used notion of stability for these systems, is the fact that the spectrum of the matrix A is all contained in the open left half plane in complex space. So in particular, when you have this property, if you write your solutions, the solution of the system, you can upper bound the solution. So sorry, here there is perhaps a typo in the sense that this is the solution, but here what I really mean is the norm of the solution should be less or equal than, some exponentially decaying term, m times e minus lambda t, times the norm of the initial condition. So this bounds the free response of the system, whereas I can bound the forced response of the system using maybe the infinity norm of the signal u. And so in particular, there will be some k big enough that can be computed from upper bounding these exponentials so that this inequality holds. So this inequality, again, let me point out here, I should put on the left-hand side the norm of phi tx0d, less or equal than this. So this is true whenever you've got stability in the sense of Lyapunov. So for linear system, essentially, whenever you've got Lyapunov asymptotic stability, you also have finite gain input to output stability. So bounded input, bounded output stability, no matter how you really define your output, which is in any case going to be a linear function of state. So you've got bounded input, bounded output stability, which comes for free whenever you've got asymptotic stability. The converse is not necessarily true. You need some geometric conditions about reachability, maybe, or detectability and things like this. But essentially, really, for linear system, the landscape of stability property is very much limited, because once you have one, you more or less you have the other. Okay, so what is interesting to remark is that, however, this type of stable behavior can in fact be quite concisely expressed by using a KL function. This is nothing but a KL function of initial conditions, of the size of initial condition, and time. So essentially, we are seeing that there is some kind of transient behavior here that can be upper bounded by a KL function of the initial conditions and time. On the other hand, there is the forced response, which potentially could be there forever. And we quantify this in terms of the input infinity norm. So that this type of term can be seen effectively as some kind of K infinity function of the norm of the input. It's a linear function, okay? But a linear function, we said, is also what we could call a class K infinity function. So why am I insisting on this? Because this, in fact, this type of inequality has inspired the definition of input-to-state stability, and in particular, the fact that input-to-state stability aims at mimicking both the internal stability behavior of the system, so quantifying the impact of initial conditions on the transient behavior of the system, as well as the external stability property of the system, so quantifying the impact of exogenous inputs. And also it's interesting to see that perhaps for nonlinear system, really one would want to have qualitative notions that should be invariant with respect to nonlinear changes of coordinates. And the fact that here we're using class K infinity functions, so we're using really a qualitative property on how the dependence from input should be, rather than a linear function. And similarly here, the way we depend from initial condition and time is really qualitative. It's increasing in x0 and decreasing essentially in t. But this makes this type of inequalities really invariant with respect to nonlinear changes of coordinates. And so it points in a direction which is quite fruitful, possibly.
I'm sorry, I have a question.
Yes.
Yeah, about the previous slide. Yeah, here. So U is BD, right?
Sorry, yes, definitely.
And when you bound by the L infinity norm,
D.
will this constant K depend on small t?
This constant K will be independent of time. It can be upper bounded by taking t to go to infinity, and you'll be able to find a bound that is independent of time.
Okay.
So thanks for the question, and sorry for the typos indeed. This is D, and this is also D, of course, from here, yeah. Okay, so this is the way we can then really define input-to-state stability. So for a linear system of equation x dot equal f of x and d, state again x in Rn and input d in Rm. In general, we say that this is input-to-state stable if there exists a function beta of class KL and a function gamma of class K infinity, such that for all initial conditions, for all disturbances d, and for all t greater or equal than 0, we have an inequality that is mimicking exactly what would happen for a stable linear system. So it's less or equal than beta, the sum of beta x0t, plus gamma, infinity norm of d between time 0 and time t. So this is exactly the same type of inequality that we had before, if you like, and so it captures the idea that there should be something transient happening as a function of the initial condition, and then perhaps eventually our state will be bounded by something that instead is only a function of the norm of the input perturbation. Notice that we don't have anything like a separation principle in here, of course, right? So there is not a meaningful notion of forced response for sure. You could perhaps define the free response, but there's no reason why a solution should decompose and add up in a form like this. This concept is fairly qualitative. It doesn't imply any kind of separation property of that sort. In fact, the sum here is just an accident, if you like, that comes from linear systems. If you like, you could, in fact, replace the plus with a max. And these two are just equivalent definitions in the sense that whenever you've got, for instance, two positive numbers or non-negative numbers, the max between A and B is really always less or equal than A plus B. So you can go from this formulation to this formulation, and in turn, A plus B is less or equal than the maximum between 2A and 2B, which then tells you that, well, from this formulation, you can go to this formulation, provided you put 2 beta and 2 gamma, which you can do because, of course, 2 beta is still of class KL and 2 gamma is still of class K infinity. So these two definitions are perfectly equivalent with respect to each other, at least from the qualitative point of view, if not from the quantitative point of view. Then, what this means, for instance, in practice, if you use the max formulation, you could draw a simple picture. You've got your initial condition here, state space, maybe two-dimensional. This is the solution corresponding to a certain input signal D. What it tells you is that your solution should always stay inside somehow the union of two envelopes. One envelope is this one, is the beta function, which is this transient thing that starts out maybe big, even bigger than x0 in general, and then decays down to 0, sorry. And eventually, though, this will become smaller than gamma of D infinity, and so eventually the solution is confined to be in this other tube, let's say, of radius gamma D infinity. And so this is the physical really meaning of the property. So some consequences of this definition. So there are many consequences that can be inferred just by looking at the definition and working a little bit with it. So for instance, trivially, we have the input to state stability implies some form of bounded input, bounded state property. So as soon as the infinity norm of the disturbance is bounded, then the infinity norm of the state, and in particular then also of the output, if the output is a continuous function of state, will be bounded. We also So we have some form of bounded input, bounded state, or bounded input, bounded output stability, as I said here. And we do not have, in general, linear gain, not finite linear gain, because the type of expressions that you can get is that x infinity is less or equal maybe than a k infinity function of x0 of initial condition plus k infinity function of the input disturbance. So even if you take x0 to be equal to 0, which is often the case, for instance, when you look at input-output operators, maybe you really look at starting out from a 0 initial condition, then this part here will not be a linear gain. You have a k infinity function of the infinity norm of the input. So this shows really how the property somehow is trying to bridge internal stability and external stability. One thing I haven't remarked, and it's remarked in this slide instead, is that the definition really for d equals 0 So when there are no when a zero disturbance is applied, or in fact when the system is autonomous, is not forced by disturbances, what this definition amounts to is simply that we have an inequality of this type, and it turns out that an inequality of this type, so a KL term alone, is really characterizing the property of global asymptotic stability at the origin of the system. So essentially, comparison functions can really be used to give a very synthetic definition of global asymptotic stability of the system at the origin, just by assuming this type of inequality. The attractivity part is trivial, because for t that goes to infinity, this quantity goes to 0, and so will this go to 0. The stability property is kind of trivial, because beta is class k in x0, so it's less or equal than beta x0, comma 0, and whenever you've got a class k function, you can invert it, at least locally, for small enough numbers, and that allows you to find how small delta needs to be to fulfill the fact that this thing is less or equal than epsilon. So this is the idea to show that this, in fact, is equivalent to global asymptotic stability. Now, there are other implications, other consequences that are written up here that are interesting to remark. So if you only look at long-term behavior of an input-to-state stable system, then you see that solutions are eventually trapped in a region whose size is proportional, let's say proportional between quotation marks, because in fact this is not a constant, but it is a k-infinity function. So it's proportional to the infinity norm of the disturbance. This property, we call it the asymptotic gain property. And this has to hold for all initial conditions and for all input signals. Another property that follows, it's not maybe completely apparent from the definition, is that you've got the so-called converging input converging state property. So not only the state will go to 0 for d identically equal to 0, but also if d tends to 0, somehow you have this desirable feature that the corresponding solution will go to 0. So a lot of the typical behaviors of linear stable systems are recovered by using this definition, essentially. Okay. So what are the major strengths of this approach is that, in fact, as I said, it can afford many linear-like dynamical properties. It is a global property. It is a natural property, in fact. If you if you start working on it, there are many equivalent formulations. We will see some of them later on. And then this approach has served as a basis for many related system theoretic properties that we will perhaps introduce briefly at the end of this seminar. One thing that is quite important and that I will like to mention soon is that for now we have a definition, but this definition needs a characterization that can be checked somehow without making use of explicit knowledge of system solutions, of course. Otherwise, this property is very hard to test a priori on a system. So we would like then to propose Lyapunov-like characterizations. So just to recap on how global asymptotic stability can be tested using Lyapunov functions, I will recall some of these results, which are by now classical. Forward implication is due to Lyapunov. Converse Lyapunov theorems were much later derived. And this is a converse and forward Lyapunov theorem expressed in the language of comparison functions, which is something which is quite customary now in the input-to-state stability world, let's say. So it's useful to see how.
Excuse me, can I ask a question?
Yes, sure.
Sorry to interrupt. I raised the
Yes,
hand
sir.
before, but probably you didn't see. I wanted to ask something, because sometimes you find a definition of monotone attractivity. Sometime I read about it, in the sense that the distance between the trajectory and the equilibrium point is monotone decreasing, right? But using this kind of definition, you're not able to capture such a property, right? Because you just look for an upper bound.
You just look for an upper bound. I have to say that monotone attractivity, in my language, would be saying that V of x, so is the constant of Lyapunov function. For that particular system, we have V of x, which is the Euclidean norm. Okay, so you have a Lyapunov function, which is simply the Euclidean norm, and that is what it translates into. So you could insist that your V of x should be the x transpose x, but it would restrict considerably the class of systems that you're dealing with. Yeah. So in here we are not indeed assuming any specific form of the way solutions should approach the origin. Yes.
Okay, thank you.
Okay, thanks. So for classical stability, then we really have that a system is globally asymptotically stable at the origin if and only if there exists a function v of x from Rn to R, which is of class C1, and in fact, without loss of generality, also of class C infinity, and k infinity functions alpha 1, alpha 2, and rho positive definite, such that these two conditions are fulfilled. So these two conditions tell us something. First of all, the first inequalities, it's like this V of x is sandwiched in between alpha 1 of the norm of x and alpha 2 of x. These two are k infinity functions. So this basically tells us that the shape of V of x, it is 0 at 0, because these two functions are both 0 and 0. It is positive definite, so it's strictly positive for x different from 0 because of the lower bound. And also what it tells us is that as x goes to infinity, this will grow to infinity. So a function like this is sometimes called radially unbounded or proper. And that's all, in fact, these two inequalities, sorry, tell us about V of x. So it has to be positive definite, radially unbounded, and this is normally expressed in this way. And then there is this other thing, which is of course crucial, and is the derivative of the Lyapunov function along the solutions of the system. So V dot of x, so the rate of variation of V along the solutions of the system should be less or equal than minus rho of x. This is a positive definite function, so V dot should be essentially a negative definite function. So this condition then are equivalent to global asymptotic stability in 0. And the advantage, of course, of this condition is that, at least in theory, if one knew how to choose V of x, they could be verified just by checking these inequalities point-wise, so state by state, taking all possible values of x, and without integrating solutions, so without explicit knowledge of solutions. And this type of results are also important because, of course, they give us some kind of robustness of behavior with respect to perturbations, for instance, of our vector field F. Now, so interestingly then, this type of approach to the study of stability can be extended to input-to-state stability. There are at least two types of input-to-state stability functions that are normally introduced. One is here, so a function, again, V of x from our state space to R, which is said to be an ISS Lyapunov function of first type, sometimes, if it fulfills precisely the same inequality as before. So it is positive definite radially unbounded, and the corresponding rate of variation along solutions of the system, so we are talking about here a rate of variation which is function of x, of course, but is also function of the input disturbance being applied, should be upper bounded by two class K infinity functions of x and gamma with a minus and plus sign in front of them. So essentially there is here a negative contribution due to states and a positive contribution due to input disturbances. In particular, when there is no disturbance, what we get is that V dot is bound again to decrease with the dissipation rate somehow, which is in fact of class K infinity. So it grows as x grows. Whereas in general, when there is disturbance, this negative contribution can be offset by a positive injection, let's say, of energy, if you like, from the input disturbance. So if you think of V as some kind of energy function, there is possibly power which is injected due to the presence of disturbances, and this can, of course, cause V to increase. In particular, here we see this because V dot is not maybe constrained to be negative, but could become positive if D is big enough. Now, so whenever you have an inequality of this kind, first of all, of course, you have the previous inequality as well for D equals 0, so you're fulfilling this. Here, notice that we only asked rho positive definite. In fact, again, without loss of generality, if you can find a function that has got rho positive definite, you can always rescale the function V in such a way that you magnify somehow its dissipation rate for big X. You just make it a bit steeper, okay, for large X, and that will increase the dissipation rate. So that will make rho bigger in turn, and so you could always get an inequality of this kind with something of class K infinity here. This is not a big issue to be done. On the other hand, when you've got disturbances, this balance is absolutely crucial, and if you've got a function here which is positive definite, you cannot just rescale the function V in order to make it class K infinity, because that will also rescale the impact of disturbances, and you will get a disturbance that whose impact is magnified as a function of X as X gets bigger. So essentially here, this type of inequality is truly crucial, the fact that we can separate the two contributions and that both of them are class K infinity. Well, in particular this one, okay? If this is class K or positive definite, no big deal. You can always upper bound it by something of class K infinity. But the truly crucial thing is that whenever X grows, this part here, which is negative, will be able to overcome the disturbance, no matter how big this is. So that's the idea, essentially. In fact, these ideas perhaps is even more explicitly expressed in this notion of input-to-state stability Lyapunov function of type 2. So we're talking again about a Lyapunov function whose shape is the same as before. What changes is the type of dissipation that we are assuming for the function. So the way the function changes in time as a function of X and D. So what we are asking here is that whenever X is big with respect to D, where the notion of being big is again expressed using class K infinity functions, so some kind of nonlinear gain. If it's big with respect to D, then V dot should be, and this is just positive definite, so should be a positive definite function. So we only really asked for D to decrease, for V to decrease, sorry, whenever X is big with respect to D. Notice in particular, if D again is 0, we are really asking this to happen for all X when D is 0, but in general, then we are asking an inequality only in a sector of the XD space somehow. So the interesting part is a theorem due to Professor Sontag and Professor Wang, who in fact introduced this concept, I studied them for many years, is that the following facts are equivalent. So the fact that x dot equal f of x and d is input to state stable is equivalent to the fact that it admits an input to state, an ISS Lyapunov function, let's say, of type 1, or an ISS Lyapunov function of type 2. So this is then a result that really opens up the possibility of checking this stability property in actual examples without trying to integrate and find out explicitly in system solutions. What's the idea? What's the key insight for a proof of a result of this kind? So the key step in the proof was to introduce some form of, let's say, to regard, let's say, input to state stability as a form of gain margin. So we start with the system x dot equal f of x and d, and we associate to this system an auxiliary system, let's say, where we do not apply arbitrary disturbances, d, but we only apply disturbances of size delta of x, norm of x, where delta is chosen to be of class k infinity, and here we put delta tilde, which is again another disturbance entering the system, but of norm, let's say, less or equal than 1 always. So we are talking here about a system which is forced by disturbances, but these disturbances are constrained to become small as x becomes small, or are allowed to grow in size as x becomes large. And the key insight is, in fact, that input to state stability is equivalent to stability of a system of this kind at the origin, so global asymptotic stability at the origin of a system of this kind, uniform with respect to disturbances d tilde. So by being equivalent, what I mean is that whenever you've got ISS, whenever you've got input to state stability, you can always pick delta of class k infinity, sufficiently small, of course. Your interest is in keeping it small somehow to be able to get stability, so that this system will be uniformly globally asymptotically stable at the origin. So why do I call this a gain margin? Because this is saying that if I bound the gain from the state to the disturbance, so in this way, like delta of x, if I bound the gain, I can close the feedback, the system in feedback with this gain bound, and I will not destabilize it. So I will get something which is uniform, globally asymptotically stable. And this is easier to study now because this is a stability property that has got something that converges to 0, and you can use similar constructions to those using standard converged Lyapunov theorems to build a Lyapunov function. And the Lyapunov function that you build for this system, it's a common Lyapunov function, if you like. It's a robust Lyapunov function. It works for all possible values of d tilde, but it's in fact what for the original system amounts to either a Lyapunov function of type 1 or 2, quite simply. So that's the key insight. So input to state stability is essentially equivalent to this form of gain margin. Of course, for linear systems, we know that whenever we've got stability, stability is robust. So small enough feedback would not destabilize it. So there is always a gain margin. And the same thing here. So we are asking for a similar property for the nonlinear systems. Now, so here I've got some simple examples really of input to state systems, input-to-state stable systems. So the first one is linear. We already said for a system like this, you can just prove input-to-state stability directly by bounding solutions using the explicit formula for the solution. If you've got a nonlinearity just in the input, that's also trivial, because you can use, again, the formula for the solution. And here, rather than having a linear gain, you will have something squared in nature or something like that. If instead you start having nonlinearities in your state as well, then really you need a Lyapunov-based proof, because non-Lyapunov-based proofs are very hard to come by. Normally they require a lot of effort, really. So for these examples, one can do Lyapunov-based proof. Now, the next one is a simple example of a system which is not input-to-state stable. I guess maybe it's obvious, but it's always worth mentioning that not all systems which are, for instance, globally asymptotically stable at the origin for d equals 0 will also be input-to-state stable. So I've put here a particularly nasty example of a system that for d equal 1, minus x and plus x cancel each other out, and what you get is x dot equal x squared, that, as you know, has got a solution which is like the tangent of t, so it's a very unstable solution. It blows up in finite time depending on initial conditions, so it's not even what is said forward complete, so its solutions do not even exist for all non-negative times. So in general, for a nonlinear system, there is really no direct connection what happens for d equals 0 and what happens for d different from 0, okay? Simply because basically you can cancel out whatever was happening before and replace it here with what is your most favorite unstable example of a system. So essentially, whenever you've got nonlinearity, really there is no, in general, no guarantee that anything can be said about the system in the presence of disturbances. But of course, in reality, things are much more benign in many examples, and to what extent they are benign is something that you'd like to discover trying to, for instance, use the Lyapunov-based proof to bound the behavior of your system forced by disturbances. So this is yet another example. Maybe P and Q could be integers, and maybe P should be odd, maybe, if we like this thing to be at least stable for d equals 0, and then you may ask yourself, what happens if I put here x power q? And it turns out that depending on what q is, you would have stability or instability. Now, for scalar system, really, things are not too difficult. We will perhaps show later on in the next few slides some examples of Lyapunov-based proofs, but of course things are more challenging in higher dimensions. For scalar system, there is really no big choice in trying to decide what your Lyapunov function should look like. It's going to be x squared always, or somehow a rescaled version of x squared. So something quite simple. Maybe you might want to take it non-symmetric, but really there's not really much use of not taking it non-symmetric. So this is how you then go about doing Lyapunov proofs. You've got your simplest possible system, x dot equal minus x plus d. You take your favorite Lyapunov function as square, compute your derivative 2x minus x plus d. So you develop this, you've got minus 2x squared, and as it often happens in ISS computation, you again get something which is a cross-coupling between x and d, and then you have to work hard using inequalities in order to maybe decouple the x part from the d part. And here you can do it quite straightforwardly, because you sacrifice a little bit of this negativity. You only get a minus 1 here, and you add a plus d squared on this side. And if you see, this is basically the inequality x minus d, everything squared, greater or equal than 0. So this technique is the completion of square technique. So inequalities of this kind are quite useful in the ISS realm. So we've got a Lyapunov function of type 1. Not always it's easy to find Lyapunov functions of type 1. Perhaps it's sometimes more direct to find Lyapunov functions of type 2. So let me show you how you can do that here. So we've got a system x dot equal minus x cubed plus d. And again, Lyapunov function x squared. Then we go about computing the derivative. And what we see is that v dot can be computed as follows, and it is less or equal, for instance, than minus 2x power 4 plus 2xd. So of course, we like this part very much because it's class k infinity in x, in the norm of x. On the other hand, we don't like this part that much. So we can perhaps rework this thing as follows. Put x here, minus 2x cubed plus 2d. And then we just essentially remark that under suitable inequality, which is this thing here, this happens. Notice I'm using here a class k infinity function of d. Because this is a class k infinity function of d, I can take its inverse on both sides of this inequality, and this inequality becomes x cubed greater or equal than 2d. And then when this happens, I have here that minus x cubed plus 2d, of course, is less or equal than 0. So I can upper bound this part with x times minus x cubed, which is whatever is left. So I get an implication of the form that I was mentioning before, that for x large with respect to the disturbance, this bit here becomes negative, and so v dot is less or equal than minus x4. So v is ISS Lyapunov function of type 2, and we can then claim that this system is ISS. In general, if you put p and q, it will depend on how you choose p and q. In particular, if q is less than p, that's fine. If q equal p already, this is an unstable system for sufficiently large d, as this part will essentially dominate the negative part that is trying to make you converge toward the origin. So yeah, so these are really the example, the simple examples I wanted to have a look at. And needless to say, I mean, proving a system is ISS in higher dimension could be quite challenging because, of course, already proving global asymptotic stability is quite challenging since there are no general criteria for choosing a Lyapunov function. Okay, so choosing a Lyapunov function is still a hard thing, especially for n bigger than 1. Okay, and it still is also in the setup of input to state stability. Of course, an ISS Lyapunov function is also by definition essentially a GAS, let's say, Lyapunov function. So the first step, perhaps, in order to try to build an ISS Lyapunov function is really trying, first of all, if you've got a Lyapunov function for proving global asymptotic stability, then you can go on trying to prove that this is also an ISS Lyapunov function. Now, once you've got a candidate D, checking that this fulfills the condition is relatively easier. The computation of v dot is straightforward, but you have to prove certain inequalities, which may not be an easy task to do in any case. For linear systems, of course, there is no problem. Everything is fine with quadratic functions, quadratic forms. There are software tools for automatic search of Lyapunov functions and ISS Lyapunov functions for polynomial systems using polynomial Lyapunov functions, but they can help, of course, but still if you don't have any physical insight into the system and there's no reason for you to believe that a certain function is going to be a Lyapunov function, these tools suffer from the fact that there are no a priori bounds on the degree of Lyapunov function that you may need, and therefore, even though you've got convex problems to check that these are Lyapunov functions, it's actually a combinatorial complexity explosion from the computational point of view when you try to parameterize these Lyapunov functions using monomials of different degrees and in all the variables and so on. Of course, the number of terms and the size of problems that you'll be dealing with will grow considerably. All right. So let me then go on presenting some other interesting variants of the input to state stability property to somehow support the claim that I had before, that input to state stability is a fairly natural property somehow, and that there are many equivalent ways of expressing it. So far, we have essentially seen the definition and a Lyapunov characterization. So two ways somehow of formulating the property, but there are more ways to do it. So the following notion is so-called exponential ISS. It was proposed by Professor Prali and again Professor Wang. And the definition is quite interesting. So we say that a system is exponential ISS if there exists beta of class KL and gamma 1 and gamma 2 of class K infinity and some lambda positive, such that this inequality holds for all possible choices of initial conditions, for all possible input signals, and for all non-negative times. So the solution here is again bounded, as for the classical ISS definition, by a KL thing, so some transient term in initial conditions fades away with time because it's KL, but something here will possibly survive, okay? And this something comes in as a convolution of a rescaled version of our input signal, again, to make notions invariant with respect to changes of coordinates, both in input and X space, if you like. Convoluted here with an exponential, negative exponential, which again gives this linear-like type of decaying memory, let's say, in the input contribution. So this is integrated, and eventually it is also rescaled by some other gain, again, because we want to make these concepts invariant with respect to nonlinear changes of coordinates. So this is an interesting definition. It's quite straightforward from the definition to see that, okay, if I now upper bound this convolution here with the infinity norm of the disturbance, as I had done before for linear system, the integral here between 0 and plus infinity of this negative exponential with something constant that can be taken out outside of the integral will be a finite number. So we get, again, a gain k times gamma 2 of d infinity, and eventually we'll get gamma 1 of k gamma 2 d infinity, which is in fact a composition of class k infinity functions, and compositions of class k infinity functions are still class k infinity. So essentially what I get is standard ISS. So from here it's very easy to go to standard ISS, whereas the converse implication is not trivial, I would say. It's not trivial to be seen. In fact, the converse implication goes through a Lyapunov construction of a suitable Lyapunov function, and a Lyapunov function of the following form. So this is as before, but v dot here, rather than having in the negative bit a class k infinity function of norm of x, is linear in v of x itself. Now v of x itself can be upper and lower bounded by class K infinity functions of X. So you could really keep upper bounding this as we would do for ISS, so replacing this with a class K infinity functional norm of X. But you wouldn't want to do it because you're really interested in this specific form, because this is a linear now differential inequality in V. So you've got V dot less or equal than minus lambda V plus gamma of D. So that this type of inequality is very helpful because it can be used to establish an inequality of this form on solution. You first get an inequality of this form of V, and then you use the bounds on V, upper and lower bounds, in order to translate this into an inequality which only needs X, okay, at time t or at time 0. So this is then a very interesting type of Lyapunov functions, and the remarkable fact is that in fact all of these things are equivalent to each other. So system is exponential ISS, the system admits an exponential ISS Lyapunov function, or the system is ISS, is input to state stable. So essentially exponential ISS, which in my opinion is the strongest looking formulation of ISS, so is the apparently stronger formulation, the one from which all other descend sort of in a trivial way, is really equivalent to the rest. And the way this is proved is in fact starting with an ISS Lyapunov function and rescaling it, so changing the way it looks like so as to make sure that the dissipation rate can be matched to V of X, so takes the same form as V of X, and this type of argument then allows you to conclude the inequality that we've seen before. One thing that is just remarked here, notice that what this is not saying is that convergence to equilibrium is always exponential. So there is an exponential Lyapunov function of this type. Of course, when D is equal to 0, this implies that V of X converges to 0 exponentially, in particular, as e to the minus lambda t. What it doesn't mean is that the state itself will converge to 0 exponentially, because these bounds here are of class K infinity nature. They are not linear or quadratic or polynomial bounds. Polynomial bounds would be good because you can invert them, and whatever converges to 0 exponentially when you apply a polynomial is still converging to 0 exponentially. But this could be functions that start out very, very smoothly or very, very steeply, okay, and so you don't really necessarily have this exponential property preservation. Okay. So I move now to talk to apparently weaker related notions to input to state stability. So there are some other properties that one can really introduce. I think this is really the apparently the weakest possible formulation of ISS, I would say. So the fact that when you look at solutions, you look at the infimum of solutions for t greater or equal than 0, you want to make sure that this is less or equal than a class K infinity function, let's say, of the disturbance D. In fact, this function doesn't even need to be 0 at 0, it could just be increasing and continuous. So that's a very apparently weak property. First of all, because we are really talking about the infimum. So solutions could really go down and up and down and up, and all we care about is that when they go down, they're sufficiently small. So apparently they could diverge to maybe infinity, for instance. So this has to happen, of course, for all initial conditions and for all disturbances, D. And now the next one, again, is a different type of formulations. It's again a bound on solutions in terms of norms of inputs or norms of initial conditions. So here, rather than having an inequality at time t, I'm somehow bounding the energy of my solution measured with respect to some class K infinity function alpha, and I'm comparing it again to the energy of my input with some class K infinity function gamma. And I have to add also a class K infinity term proportional to initial conditions, because we said in the input-to-state stability setup, we are not always starting out from state 0, like maybe you could do in operators. So when you look at this situation, you're really mimicking an input-output type of bound, energy of state or of output, if you like, less or equal than energy of input. But we make these definitions flexible by allowing here arbitrary class K infinity functions of inputs and states. And that's a type of integral formulation. So it turns out that this result that I could call, perhaps I could name everything is ISS theorem. It's an interesting result really by Professor Sontag and Wang that shows that input-to-state stability has so many equivalent formulations. And some of them are listed here, but there are many others really. I'm listing here the most important. So for instance, asymptotic gain that I mentioned before, plus local Lyapunov stability. So truly for D equal 0, local Lyapunov stability and asymptotic gain. So notice that this is, if you like, the analog of saying that global asymptotic stability is the same thing as attractivity and local Lyapunov stability. So local Lyapunov stability is here, and what asymptotic gain is nothing but an attractivity property for systems with input, except that this time the attractivity is not to 0, but to a neighborhood proportional to the size of D. So that's kind of a result in the same spirit as that.
I do. I think
yes?
there might be a question. I don't know how long it's been up.
Sorry, I didn't notice, sorry.
Just on the previous slide, on slide 32.
Which slide? Sorry.
32, where we have
yes.
weaker definitions. So in the first definition, we say that it's a weaker definition only because the solution is bounded by the K infinity function on the disturbance.
Yeah, it's a weaker, it's in fact apparently weaker, I should say, because we are assuming a bound on the infimum of the solution, all right, as t greater or equal than 0. So it's the infimum. Notice that this bound would trivially hold if I took the limb sup. The infimum is less or equal than the limb sup for t that goes to infinity, and that is less or equal than gamma d infinity. So the so-called asymptotic gain property, this thing implies asymptotic gain, for instance. At least if you take gamma to be 0 at 0. It's apparently weaker because we are really only constraining what the solution does along a sequence of times, perhaps, where it assumes its local minima. So it apparently, at least, leaves a lot of freedom to what a solution can do. But we have to keep in mind that we are asking this property for all initial conditions and for all input disturbances. So we're not asking it on a single function. I would say on a single function, this is truly a very weak assumption, because it's an assumption on what it does along a sequence of time. So it's very easy to build signals that have got the infimum bounded, but the supremum is not bounded, for instance, okay?
Okay.
So it's an apparently weaker notion in this respect. So the result here tells us that, in fact, a lot of these properties are equivalent to input to state stability. So asymptotic gain plus local Lyapunov stability, and then this inf property that I was just talking now, plus 0 global asymptotic stability. We need global asymptotic stability in the absence of disturbances because we haven't really assumed that function gamma to be class K infinity, so we haven't even assumed that for d equals 0 things would be fine. And then the integral formulation that I showed before, energy to energy bounds are also equivalent to input to state stability, or bounded input bounded state stability plus 0 gas, so another alternative way of looking at things. So there's many possible ways. So that really kind of shows that it's a fairly natural concept, I would say. So this example instead are meant to show that, yeah, well, everything is ISS, but perhaps not quite in a sense. So these are very simple counterexamples, but also quite significant, I would say, for applications. So if you think of any systems x dot equal minus saturation of x plus d, this saturation, of course, has a limited range, and therefore the disturbance here, if it's sufficiently big, can overcome whatever number the saturation is given here, and so can steer the state of a system to infinity. Okay, so and that violates, of course, input to state stability, even though for d equals 0, this system is very good behaved, so it's just globally asymptotically stable at the origin. So this could be seen, for instance, as a single integrator is being controlled with a linear feedback, but the linear feedback, in fact, is not truly linear because at some point the actuators have a saturation, and so they are not able to compensate for disturbances of arbitrary magnitude somehow. Or also we could have a second order equation here, maybe there's some variable, a double integrator y2 dot equal u, and you control it again with a linear feedback minus y dot, which is a stabilizing feedback, linear feedback. But then again, you put a saturation, and then you ask yourself, is this input to stay stable? So it turns out that the saturation is benign when it comes to global asymptotic stability. You can still prove that for d equals 0, this system, despite the presence of saturation, is globally asymptotically stable, but in fact, it is not input to state stable, of course, because the disturbance can again overcome here the saturation and then steer the double integrator wherever it likes it to. So indeed, ISS, everything is ISS, but it's a strong requirement. So it's a very natural property, but it's also a rather strong requirement in many situations, also because it's a property which is global in nature. Here again, it's a simple example, a system which is good for d equals 0, but if you take d equal 1 or 2 already, you can see that this behavior, you won't have a stable behavior. So these systems, which are not input to state stable, still are quite important in applications, and they are still exhibiting some form of robustness to disturbances. So we would like to perhaps try to capture what kind of robustness to disturbances these systems may exhibit. Okay, so perhaps I could, since I've seen that enough time has gone by, I could, before starting with the new concepts, I could stop here for a little break, and if